Consider a hydrogen atom, which is modelled by a nucleus containing a proton and an electron orbiting the nucleus like the planets orbit the Sun. So this is our Bohr model. And we saw that energy transfer occurs when photons are absorbed or emitted by an atom. So for example, if the electron absorbs a photon, and this photon is carrying an exact amount of energy, then the electron will jump to an energy level. So this can be either of the allowed discrete energy levels, in this case for hydrogen. So energy can be absorbed or emitted by an atom only if this amount of energy corresponds to the energy difference between two atomic energy states. So for hydrogen, we have n equals 1 being the ground state, and n equals 2, and so on, are the excited states. So recall our energy equation for a particular state n is equal to the energy of the first state on n squared. So we can have infinitely many states. So as n goes to infinity, En approaches 0. So given that an atom in a given energy state may absorb a photon with the appropriate energy to transition to a higher energy state, as we saw, where the electron absorbs a photon and jumps to the appropriate energy level, if the photon is carrying that amount of discrete energy, an atom in the excited energy state can emit a photon of the appropriate energy to spontaneously move to a lower energy state. So the electrons in the excited state will want to jump back down to the ground state, which is the most stable. So therefore, these electrons emit a photon. So if the electron is at this energy level, it can jump back down to this energy level, or the energy level corresponding to the ground state of the atom. So given we modeled the atom as a system consisting of an electron and a nucleus, a change in energy state of the atom corresponds to the change in the interaction energy between the electron and the nucleus, given by this equation. Now consider the case where the excited electron drops to a lower energy level, so therefore it emits a photon, and therefore the energy of the emitted photon is equal to the change in energy between the two states. So if an electron, for example, jumps from n equals 3 to n equals 1, then it emits a photon, and the energy of this photon is E3 minus E1. So in general, the difference in energy between two arbitrary states is equal to the energy of the state with the higher energy minus the energy of the state with the lower energy. So remember that the energy of state 1 is minus 13.6 electron volts, and dividing by n squared, the energy of state 2 is minus 3.4 electron volts. So the energy of the states gets higher and higher up to the energy state where the electron is ejected from the atom. So recall that the energy of a photon is Planck's constant by the frequency, and given the speed of light, which is the speed of the photon, is equal to the wavelength by the frequency, then we can write the energy of the photon as Planck's constant by the speed of light on the wavelength. So on the left hand side, we have hc on lambda, and on the right hand side, we have the energy of the higher energy state being equal to the energy of the ground state divided by the index of the higher energy state squared. And the energy of the lower state is E1 on the index of the lower energy state squared. So therefore, dividing through by hc and factoring out E1, we get the reciprocal of the wavelength of light is E1 on hc, while the reciprocal of nh squared minus the reciprocal of nl squared. And now if we take the negative of this constant as the Rydberg constant, so recall that we calculated the energy of the ground state in joules, which was negative 2.179 by 10 to the minus 18 joules. And the Rydberg constant is the negative of that. And that's divided by Planck's constant by the speed of light in a vacuum. So we had Planck's constant was 6.626 by 10 to the minus 34 joule seconds, and multiply by the speed of light in a vacuum, which is 2.998 by 10 to the 8 meters per second. Now let's make a bit of room. So therefore Rydberg's constant is around 1.097 by 10 to the 7 meters to the minus 1, which you can verify using the appropriate units. So this expression over here, being the Balmer-Rydberg equation, can be written using Rydberg's constant. So we have minus r here. Now let me remove this. So the visible wavelengths are obtained when the atom transitions from the excited state 3 to 2. So if you substitute NH equals 3 and NL equals 2 and solve this equation, and converting the wavelength to nanometers, you'd get the wavelength is 656 nanometers. And if the electron jumps from the energy level n equals 4 to n equals 2, so you could substitute NH equals 4 and NL equals 2, and what you'd get is 486 nanometers. And similarly, from 5 to 2, you get 434 nanometers, and the wavelength from energy state 6 to 2 is 410 nanometers. So you can see that this corresponds to a red wavelength, and this one here corresponds to green. This wavelength is blue on the visible light spectrum, and this one here is violet. So if you did the same calculation for an atom that goes from energy state 2 to energy state 1, you'd get a wavelength of around 122 nanometers, and this is outside the visible light spectrum, so you can't see it. So this is a continuous light spectrum that consists of all wavelengths of visible light, and we can see that the emission spectrum of hydrogen is discrete, so only certain wavelengths of light are emitted, and we'll look at this in more detail. The atoms of each element have a unique set of allowed energy levels, as we saw for the hydrogen atom, and thereby a unique set of absorption and emission frequencies. So recall that using the Balmer-Rydberg formula, we determine the wavelengths of the emitted photons for hydrogen, where the hydrogen atom transitions from higher energy states to energy state 2. So in that case, where the electron jumps from energy level 3 to 2, we see a wavelength of visible light. And similarly, where the atom transitions from energy level 4 to 6 down to 2. So this would result in visible wavelengths of light being emitted. So we can construct an emission spectrum to determine the elements in a source of light. So if we run this experiment over here, so we run a current through a gas discharge tube. So in this case, this tube contains hydrogen gas. Then this will excite the electrons. So they'll jump to a higher energy level. And therefore, given the electrons will want to return back to the ground state, they're going to emit photons. And these emitted photons hit a screen. And the wavelengths of light that are emitted correspond to these discrete wavelengths in the visible light spectrum. So we'll only see these wavelengths of light being emitted. So this discrete spectrum is the emission spectrum of hydrogen. Now on the other hand, to obtain the absorption spectrum of hydrogen, we can shine a beam of white light through a container holding the hydrogen gas. So in this case, the electrons in the ground state absorb a photon and they jump to an excited state. So therefore in this case, we see a continuous spectrum with dark spots corresponding to the wavelengths of light that were absorbed by the hydrogen atoms. So again, the absorption spectrum is continuous with dark spots, whereas the emission spectrum is discrete. And as we've seen, energy level diagrams are commonly used to visually represent the energy states of an atom. The binding energy is the energy required to remove an electron from an atom, causing the atom to become ionized. So for example, if the atom was in the ground energy state, so the electron is in the first orbit, then if the electron absorbs a photon carrying 13.6 electron volts or greater, then the electron will get ejected from the atom. So note that if the atom was in this excited state, corresponding to the third orbit, then it would have to absorb energy equal to 1.5 electron volts and greater for the atom to be ionized. So an atom in the lowest energy level or ground state will require the greatest amount of energy to remove the electron from the atom. So recall that the energy of a photon is Planck's constant by the frequency, and given the speed of light is the wavelength by the frequency, then we can write this as Planck's constant by the speed of light on the wavelength of light. So the energy of the photon is equal to the kinetic energy of the ejected electron plus the binding energy required to ionize the atom. Consider the energy diagram for hydrogen if the atom is in the excited state, with the electron in the third energy level. Determine the possible wavelengths when the electron drops to a lower energy level and a photon is emitted. So the electron can drop to n equals 2 and n equals 1 in this case. And which wavelengths of emitted light are visible according to the electromagnetic spectrum shown here. And the Rydberg constant is given. So recall the Balmer-Rydberg equation was the reciprocal of the wavelength being equal to minus the Rydberg constant by the reciprocal of the index of the higher energy level squared minus the reciprocal of the index of the lower energy level squared. So the reciprocal of the wavelength as the electron drops from energy level 3 to 2 is minus 1.097 by 10 to the 7 multiplied by 1 over the square of the higher energy level minus the reciprocal of the square of the lower energy level. So if you solve for the wavelength, you get 6.56 by 10 to the minus 7 meters, and multiplying this by 10 to the 9 gives 656 nanometers. And similarly, you can determine the wavelength of emitted light when the electron drops from energy level 3 to energy level 1. So in that case, NH is still equal to 3, but the lower energy level will be equal to 1. So that gives you a wavelength of 1.03 by 10 to the minus 7, or 103 nanometers. So this wavelength of light is in the visible light spectrum, so it's a red wavelength. And this wavelength of light is not visible, so it's in the ultraviolet region of the electromagnetic spectrum, as it's a smaller wavelength than 390 nanometers.